Hello students, we were discussing the serial active search code acquisition technique for FFH MFSK system. Today we will do some analysis on that code acquisition mechanism for FFH MFSK. Quickly we will revisit the block diagram that we were discussing. You have seen this block diagram in the last module, where the incoming signal YT was getting mixed with the locally generated PN sequence and which is also driving the frequency synthesizer. We understand that this is a frequency hopping communication mechanism. So, frequency synthesizer will be generating the hopping sequence, and it is a fast frequency hopping mechanism. That means that within a symbol duration or tone duration, there are multiple hop frequencies over which the same signal is spread. And we have utilized the MFSK signaling mechanism. That means, for transmission of a typical symbol, we have a set of the tones from where actually for a typical symbol a typical tone is assigned. So, we are dealing with now two different frequencies. One is the modulation frequency, we call it modulation tone, and another is the hopping frequency, which is actually the frequency that is getting generated locally here in the receiver, and the pattern of that generation will be governed by the secret key, and frequency synthesizer will generate that hop frequency. So, these two different frequency terms that are there inside the incoming signal, we are now multiplying with the mainly the hopping frequency to de-hop the signal. So, this is a spreader or the mixer, whatever you say, and the signals are actually then passed through a band pass filter having a bandwidth of capital B. We saw that then the filtered signal is passed through a correlative. It is a non-coherent detector architecture. So, this NC stands for the non-coherent demodulation architecture, which demodulates at the frequency of the IF frequency plus the symbol frequency or symbol tone frequency. We understand for different symbol we have the different tone associated with it. So, the center frequency of the demodulator, so there is a bank of demodulator, and the center frequency of each and every demodulator is synced with the different frequency stages of the frequency modulation tones. And any one of the at a particular moment, any one depending upon which symbol was transmitted, hence which modulating tone was transmitted, any one of the demodulator architecture output will give you the maximum or the peak at a particular time, and hence this maximum is picking up over a duration of n into th, I mean equal to the symbol duration. You will select any one of these bank of the modulator output, and then it will be threshold compared and will adjust or update the clock. That was the block diagram as we understood last time. Based on this only, today we will try to write down the equations of y t, x t, and then try to find out z t, and we will try to realize how that the output, the acquisition mechanism is obtained. So, from here we also understood the time frequency diagram of this fast frequency hopping MFSK signal. The diagram will be little bit changed if you change the system from fast frequency hopping to slow frequency hopping. The diagram that I am showing here, it is basically the fast frequency hopping. What we found that is this was a MFSK sequence, and these are the frequency of each sequence coming, and the transmitted hop sequence was given by F1 to F4. So, within the duration of one MFSK symbol, you have the 4 hopping frequencies. So, the hop frequency is 4 times higher than the symbol frequency, and the received FFH MFSK signal hence will be governed by the FSK plus F1 plus some del F is contributed by the Doppler effect of the, and which Doppler effect comes between transmitter and receiver if any one of them are moving or both of them are also moving. And that we understand that the Doppler frequency, as if the speed is constant for the receiver or the transmitter, then the Doppler frequency we have assumed to be added as a constant fashion in each and every received sequence interval. And we also assumed that local synthesizer, frequency synthesizer of the receiver is not properly time matched with the transmitter frequency synthesizer, and hence there is a time error also associated with it. So, this diagram completely talks about that there is a time error associated given by EPSA, and there is a frequency error associated given by the Doppler. And hence the receiver frequency synthesizer, because of this error in the time domain, all the frequencies will be shifted in this fashion, and hence you will get the mixer output, the mixer output of the receiver frequency as well as the receive signal and the receiver locally generated frequency synthesizer output, after multiplication in the mixer, and the output of the mixer you will be ending up with this FIF, because your incoming signal is F1 plus FSK plus del F, and the frequency synthesizer is generating a frequency of F1 plus del F. So, after bitting you will be left with FIF plus this del F plus this FSK. So, like that all the patterns will come serially, and remember one thing, the decoded output will be high only for the duration over which that overlapping is happening. Overlapping of the difference frequency mixer output and the received signal, whatever be the time axis overlapping is there, for that duration only the decoder will be able to give you some output. In this assumption, we have assumption that it is 4 times. Remember, the 4 times is the hopping frequency than the incoming frequency. Assumption number 2, we have a Doppler contributed by del F, Doppler frequency, and we have a timing error attributed by EPSA, and hence we understand that the frequency previous to this point of the context or point of our interest, and the frequency next moment and next instant, both will be different than the current hopping frequency. So, the hopping frequency at the previous section and the hopping frequency and the at the next section, they are different at any moment, and you will be able to get the output of the detector wherever the overlap will be having only. We may come back to this diagram if we have some confusion in the successive section. We will start with the signal, the transmitted signal defined by yt over 1 symbol duration, and yt is here. Okay. So, we are currently writing the equation for yt, and yt is given by log square root of 2 pt minus ita summed over I to capital N and cos of omega I plus omega s j t plus theta I. Remember, this pt is the power of the transmitted signal, as well as we are considering that this is a received signal power. Th is the hopping duration, pt is a basic waveform, cheap waveform. Omega I the index I corresponds to the hopping frequency at the ith moment, and j is the index of the modulation tone frequency associated with the current symbol. So, I will be telling which hopping frequency you are in, j will be telling what modulation tone you are dealing with. So, remember, over a particular duration of the symbol, the j won't change, but I will keep on changing, and we are considering that per symbol we are having capital N number of the hops. So, this hopping frequency will change from I to capital N with a constant of S j. That is the meaning of fast frequency hopping, we understand. And these are the frequencies expressed in the radian, and angular frequency is expressed in the radian per second, and theta I is the corresponding phase with respect to the hopping frequency I. Remember, we consider that we cannot actually guarantee that whenever hopping is going on, there will be a same phase relative to every hopping. That's impossible. So every hopping is associated with some amount of the different kind of the phase associated to that. So that can't be guaranteed. That's why theta is also varying with respect to your index, hopping index I. And expression for your omega I and omega S, as I expressed, they should be equal to 2 pi f I and 2 pi f s j. So this is a signal that has entered into the front end of the receiver, and this is actually the signal transmitted also from the transmitter. Next slide. We have seen that PT is nothing but the pulse given basic pulse shape, and we will redefine what is the meaning of this PT is here. PT is nothing but within this hopping duration, PT's value will be equal to 1, otherwise PT will be 0. And if we assume that the received signal is also affected by the Doppler frequency, and it is having a Doppler shift of del f, and there is no timing delay associated with it. If I first only introduce changes due to the Doppler shift, then the received signal y dash t will be written as like this. Remember that earlier wi plus wsj is getting associated with another shift attributed by the Doppler shift of del f, and now we are also associating the noise, incoming noise associated with that. And remember, this is an additive wide Gaussian noise process, NT is, and NT is having, it is a complex Gaussian noise. So it is having a cos as well as sine, in phase and q phase component written here. And remember, like others two guys, we have added, we have represented Doppler shift in terms of its angular domain, and del omega will be represented by 2 pi del f. So now the equation 1.1 is now changed to 1.3 when Doppler shift is added or contributed into the received signal model, and noise is added, complex wide Gaussian noise is added also. After that, when the dehopping will be happening, the dehopped signal, the xt, that signal will be looked like the, there is a, we understand that in the dehopped signal we cannot omit the error that we have considered in the time frequency diagram. The error was in terms of ipsa, and when the dehopping will be done, if that synchronization is not done, time synchronization between the frequency synthesizer of receiver and the frequency synthesizer of transmitter is not re-established, the received signal, dehopped signal, will reflect that error definitely in the time. So t minus kth will be further delayed by this error, time error, and you will be also ending up with the related term coming from the frequency section. And this is the kth for the kth frequency we are dealing with, and we are having the intermediate the IF frequency ended up with after the mixer is multiplied and the bandpass filter has done its job, and theta r is the remaining amount of the phase or the remaining phase associated with the dehopped signal. Remember, if this delay, this relative delay, it is relative to the receiving hopping signal, it is assumed that this delay is not large than the hopping interval or hopping duration th. So we have considered that we will get the dehopped signal, the decoder output will be able to give you something, some output will be coming out only if your error is less than equal to the hopping duration. If this hopping duration, if it crosses the hopping duration, then it will be considered that no signal at all correlation will occur over the, because there is no common overlap and you will not get anything at the output of the decoder. So the perfect 0 is expected to get at the output of the detector. We understand that the incoming signal is now having a Doppler effect, having a time error effect, and so the mixer output ZT the mixer output will be showing, if I try to see the incoming signal with this all this kind of the errors associated with it, we will be able to see that the mixer output is now will be reflecting both the Doppler error or the effect of the Doppler, as well as he will also reflect the error of the timing. And this has got expanded because we have also incorporated the noise, complex Gaussian noise term. We have also got a new term here which is called the OX, which denotes the order of the, it denotes the term of the order of this X. And remember this phi IR, what we are seeing here, the related is the equivalent error in the phase, it will be given by the theta I minus theta R, I mean receive associated phase associated with the ith hopping and the received phase, plus the omega I minus omega f into multiplied by the epsilon term. And if I consider that the error is less than this timing duration, hop duration, then the double frequency term will be coming up, and so it will be collapsing to the single sum like 1.5. So, fundamentally this is the term that is coming up at the output of the mixer because of the presence of the both frequency error as well as the timing error in a FFH MFSK signal. So, now we will enter into the detector section, and we will try to see that if I now detect it, I mean in the detector it will multiply with the signal in the ith path as well as in the qth path by the in phase and the quadrature phase component. Remember the detector, prior to the detector there was a band pass filter, right, and the band pass filter has filtered the incoming signal at the frequency of FIF or equivalently omega IF, the term we have seen in the ZT. So, if it is tuned to omega IF, so this decoder will also be tuned at IF plus the frequency, angular frequency of the modulating of the modulation tone, and both the in phase and quadrature phase will be created, and we will be continuing the in phase and q phase integration and square. It is basically the correlator architecture, multiplication and integration, and then the squaring it up with the envelope detector output we will take, and finally adding up both the term we will feed it to the decision device. Here remember that based on the choice of the band pass filter frequency or intermediate frequency, it is the intermediate frequency that we are choosing, and based on the IF filter we are here also the synchronization with that IF filter needs to be established by the decoder. So, decoder does what? Decoder takes the incoming signal from the IF filter, and he creates the two paths. He creates he separately operates over the in phase as well as the q phase part of the incoming signal, and does the integration, sampling, and square law envelope detection. It is basically because it is a non-coherent detector going on, and we will see actually the mathematical output of this detector. Let us first consider over the upper term. The upper term is the in phase path coming inside the detector. This in phase path will be, we understand from the last equation 1.5, that with the in phase path now the detected signal, I mean the cos that section will be multiplying, and if my cos let us go back, if I multiply with the cos to omega IF plus omega SL, and we had earlier the terms of omega SJ, omega IF and del omega, then we will be ending up with omega SJ plus del omega plus omega SLT, and omega IF term will be going out because they will be butting with each other. Similarly, for the noise terms also you will be seeing the same kind of the operation is going on, and this sum frequency again the sum frequency in the higher part is neglected since they will be filtered out in the correlation process. Similar to the ith part, in the qth part also you will be seeing the same kind of the expression, but these are the q phase components, all the sign components will be reflected here, and the original signal section, the upper portion which is the signal section, he will be out of the intermediate frequency term. Remember, if you look carefully in that in phase and the Q phase term, they are divided into two halves. The first half is basically the signal section, the lower part is basically the noise component. So, in next slide we will write down this I and Q component as the IS plus IN. And remember that we can easily show that the summation multiplying by the noise terms, this guy, the noise terms multiplied with this sum term, actually it forms finally a constant, and it is as it is a wide Gaussian noise. So, it will be scaled by a factor of 1 by root 2, it is easily provable. And as I told in the last slide that each of these in phase and Q phase components are combination of the noise section as well as the signal section. For the noise associated with the in phase, we will mention it as NIT, and the noise associated with the Q phase, the whole term will be now considered to be NQT. If we consider that the first one to be IS, then obviously you can write down 1.8 and 1.9 as 1.110 and 1.11 simply. And now this let us look inside this noise terms, and remember these two noise terms, if I see the what is coming for these noise terms at the output of the correlators, the correlator will take individually both of them, and it will integrate over the interval of our interest, which is the hopping interval, and average it out. And if we do the same for the I and the Q phase, we will find that the variance also can be easily calculated, and both the variances for the two paths will be equal and will be given by the eta 0 by 2 by Th, where eta 0 by 2 will be your two-sided power spectral density of the noise, wide Gaussian noise, and Th is our hopping duration. It follows also that if I now look in, that was the noise section. If I look now into the signal section, the signal output, the signal component will have the output of my this adder circuit. So, this will be IS square for the signal section, this will be the QS section square, and this will be the adder, it will be added up here. So, this adder output now we are looking into this equation 1.15, and definitely it will be the individual integration and then squaring up. So, correlation and then the squaring up according to the architecture. It will be a first correlation, it will say integration part, then the sampled integration part is getting squared up for both the paths. So, the same thing we have done in the equation, nothing else. And if you solve it by substituting the values of the IT and QT from here, equation number 1.8 and 1.9, where we will be ending up? We will be ending up with this equation of the P sign of this guy. Capital P is the power of the transmitted signal. Del F we understand is the contribution coming from the Doppler frequency or the Doppler shift. FSJ is the frequency associated with the jth modulation tone, and remember this L is the frequency associated with the Lth modulation tone. Actually, this substitution is coming because of this errors, del F error, as you are actually may get some interference from the neighboring modulating tone, and so the difference of these two tones will be reflected in the computation of the IS square plus QS square. Also, you will be able to see that there is a contribution from the timing error section, and so it won't get multiplied directly with the Th square. There is a difference between the remaining time period for which actually detector is creating the output. This is the remaining time interval that is coming into consideration in computing the IS square, the total value of signal component. And the correlation of this frequency hopping signal for a frequency error del F and a time error epsa, it is equivalently same as if when P is considered to be 1 and if FSJ and FSL are actually considered to be same. I mean, there is no ambiguity, and we could properly select the modulation tone in the receiver if that is the situation. Then this whole equation will look like this. We call this factor as ambiguity function. So, we will coming down here considering that my error, the timing error, is much less than the hopping duration, and this ambiguity will come down here, considering that my p is equal to 1 and then there is no ambiguity from the FS and FSJ detection. When this transmitter's modulation frequency is same as the receiver symbol frequency, that is situation when this FSJ and FSJ is equal to FSL, and so that this square root of this term will now come to this fact if p is not considered to be 1 definitely. So, it will be coming like this. And now consider a case when the frequency error time times hop duration, this frequency error times this hop duration, I mean th minus this guy multiplied by this frequency error time, it is so very small. It is so small that in the it is very small compared to the unity, and the timing error is also very small compared to 1 hop time. So, this is close to very small, close to unity, and this is very small compared to this tau h. If this is the situation, and we assume that this non-coherent FSK modulation is going on, and we are thinking that the modulation tone are kept in such a way that the minimum gap between two tone, the nearest tones is they are separated by 1 by th Hz to ensure the orthogonality. If we consider like that, then this ISS square by QSS square, the signal component will be boiling down to this guy. And it can be easily understood that when FSL is being detected by the demodulator for FSJ, when FSJ transmitted but FSL we have detected, then we will have almost no component kind of at the output of the detector, because this difference will be coming almost 0, and then you will be ending up with the perfect 0 situation because of sin n pi is equal to 0. So, basic point is that the detector is the output is coming perfectly 0 and you are not getting anything if the tone frequencies or modulation tone frequencies are not matching, and desired signal you will only getting non-zero response only you are getting when the time frequency errors are, basically the condition is time frequency error should be very small, and you will be getting at the output with the for the desired signal only. Otherwise, actually the desired signal output is expected to get 0, complete 0 if the time frequency errors are significantly high, and also the modulating tone frequency that you are developing is not properly chosen in the receiver circuitry.